exploration is a legitimate role of government, and I would like to see it do it well. And it's not exclusive. You know, if sources other than government begin to do more things in human spaceflight, that will empower, not disempower, more achievement by the government space program. Having said all of that, the truth is, I'm tired of talking about the ways that NASA could do better because there's no evidence that they're going to. I wish that were different. And it can be different anytime that our national leaders decide to make it different. And I've talked about settlement and why I think that's where we as a movement and we as an industry need to be going. And of course, what I do 99.9% of the time is work on space transportation, because cheaper space transportation is the tide that lifts all boats. The cheaper space transportation becomes, the more we can do of everything in space, and that's what I spend my day job on. But between settlement and trucking, there does come the day when the first human beings set their feet upon some place that people have never been before. And if we can't figure out how to get the first people there, getting the 100th people there so that they actually have a colony or a settlement that they can set up isn't going to happen. And I'm frustrated that our government space program is currently not strongly motivated to do those things. And I don't want to give up, and I don't think we have to, and that's really the point of the talk. And if you had asked me 6 months ago, is it really practical to think about non-government entities doing exploration as opposed to economic use, human exploration of new targets, I would have said, I don't know, or which would have been a polite code for probably not. But I've continued to think about it, and nothing I'm about to say is original. There are no new ideas in space, because everything's been thought of somewhere. I don't know where all of it's been thought of before, but I'm sure if you look hard enough, it's all been thought of before somewhere. But I do talk to a lot of people in the industry, and I do maybe have a little bit of perspective, and I get to see into a lot of stovepipes of people who aren't talking to each other. And maybe if we put those pieces together, and maybe if we start talking more openly in the community and to each other about all the ways in which the rules that we're used to can be broken, maybe the belief will start to spread that we can actually do these things, whether the government chooses to play a beneficial role or not. And then maybe if that's true and we start doing some of them, government will choose to play a beneficial role. That would, of course, be a wonderful thing. The tremendous revolutions that you've been hearing about today in what's going on in unmanned space activity are all, in one sense or another, driven by ways that we can do things smaller and more cheaply than we otherwise would have been able to do before technology advanced. It's not because space transportation's gotten better. We're working on the problem, but it hasn't gotten a whole lot better yet. But if you can do with a kilogram what you used to take a ton to do, that obviously empowers more users of space, whether space transportation has improved or not. At first glance, it would seem that human exploration is not such a ripe field for that. We come in somewhat standardized pieces. There's a limit, to how far down we can scale, although I keep trying. But I think there are things that you can scale down that change the rules and what a human mission would look like. You can scale down mission assurance. It's been pointed out that private sector efforts by their nature are more risk tolerant. That's because in the private sector markets, you assume that 10 companies are going to try things and 8 of them are going to fail spectacularly and one of them is going to sort of muddle along and maybe one of them will succeed spectacularly. Governments don't work that way. That's not a criticism, that's just a fact. You can scale down the number of people that you take. The trend in government space mission planning has been to assume that you need ever more people. There is some discussion about whether the minimum number of people that you want to scale down to is 1 or 2, but it is 1 or 2. It is not 7 or 4. That's a difference that makes a big difference. You can scale down the size of the step that you take. Again, the focus on government space planning has been, we went to the moon 6 times, or 5 times, I lost count. Therefore, we must next do something that is enormously more ambitious than that, without a corresponding increase in the budget to support that. That's hard to achieve. And the other element, which is perhaps not a scaling down factor, but if you look at most past exploration efforts, most of them historically have mostly used the ships we've got. Lindbergh may have gotten a new airplane to fly the Atlantic, but he did not invent a new airplane engine or a new airplane technology to do it. Admiral Byrd flew over the poles for the first time with conversions of airplanes we've got. The Nina, Pinta, and Santa Maria were not purpose-built craft. So there's an enormous step down in the size of the mission you can take by using pieces. But the converse of that is I don't think the human spaceflight community has fully understood the implications of what's been going on the last 10 years in both unmanned space and in smaller space companies. It's not just that these companies are figuring out how to do things cheaper. They're also figuring out how to develop things cheaper. So the flip side of wherever possible, use the stuff you've got, is where it's not possible to use the stuff you've got, don't be afraid to make something. And I've seen a lot of efforts to discuss how could we do human exploration radically differently, get stuck on the boulder of, oh, but that would involve building something new, and we all know that takes $10 billion, and so that just can't be done. Well, you know, that same logic would have said that many things that have been done in the space field in the last 10 years can't be done, and nevertheless, they still move. I'm going to throw a few slides up, but I'm going to skip most of them and flash them only briefly because I hate talking to slides, but they'll be available afterwards for anybody who wants to go back and read the fine print. And so my answer to this question is, I can't prove that human exploration without NASA or without other government efforts is possible. What I can do is try to convince you it can be done for about 2 orders of magnitude less than historically has been assumed to be required. Now, is 2 orders of magnitude enough? I don't know the answer to that question. I am not good at dreaming up inventive business plans or talking to people who have billion-dollar checks to write. But there are other people who are good at that kind of thing. I hope some of them will hear these words and go out and say, if the engineers have not figured out how to do it 100 times cheaper, maybe I can figure out how to do something with that. Except that the clicker doesn't seem to click. Is there somebody back there who can flip the next slide? The big green forward button doesn't seem to do anything. I'm not going to read the slides, but I will carry on until we can get the next slide without it. Okay, the first thing you do when you start looking at how you're going to do a private manned mission or a manned mission, but not with all the NASA rules, is it all gets sized by whatever you use for an Earth departure stage. And I'll consider for purposes of this discussion until the end living within the means of the Earth departure stages we've got. There aren't that many of them. It's not that we can't make new ones, but if you want to start planning a mission right now, which is generally the business mode that people are in, if they're thinking about a private thing, they want to start right away. It's hard to start by saying, first you change the kind of vehicles that you have, and then you start thinking about how to plan the mission. And for technical reasons that I would take time to explain, if it's not a hydrogen upper stage, it just doesn't play. There just is nothing else out there that competes. Now you can play lots of games with this. You can put up a refrigerator or a sun shield or something that lets you increase the coast time that you can use for a hydrogen upper stage. You can do what I've come to call buddy tanking, where you launch more than one of them and you use one to top off the other. And you can play games with putting other kick stages underneath them, but that doesn't help you on a cost effectiveness basis very much. So next slide, please. Or clicker if that's working. Or previous slide, please. There we go. There's just no way to get that one. There we go. So here's a quick summary of the Earth departure stages that are out there now, and how much they can get out of them in terms of dollars per kilogram to Earth escape. Nothing magic about that, but it's a relevant metric for what you can do. And of course, anything I say about the price of any launcher is a little bit quibbleable because they're not exactly catalog items, but they're my best guess about how you compare an apple to an apple. And quickly you find that nothing beats a Centaur in terms of dollars per kilogram. and that if you want something bigger than a Centaur, Delta IV Heavy is about the only way to go. Now, there are other things out there that are in development, but again, that's what we've got right now. So you can put up a fairly significant payload with those. And what's interesting is that if you launch those stages on the launchers they go on with no payload, they come up pretty close to full. That is not immediately obvious, but it is true. So you can launch a Delta IV Heavy upper stage on a Delta IV Heavy as a full Delta IV Heavy upper stage. And you can launch a Centaur on an Atlas 551, and it pretty much comes up as a full Centaur. So the first trick you play is you use whatever launcher is cheap this month to launch your payloads, but whatever launcher comes up with the big-ass hydrogen stage, you use that to get your Earth departure stage up. Then, of course, the two of them have to get together and have a party in Earth orbit and go wherever it is that you're going. The second thing that you find is that every human mission that I've ever seen a plan for involves some kind of capsule or vehicle that you bring the people back to Earth with. And all of them that are out there now are way too heavy to do these kinds of missions with. So the first piece that I think we have to embrace the necessity to build is we need, if you're going to do minimum size missions with what I'll call 2 people, you need a minimum size capsule. I think we have an existence proof that that is an artifact that can be done for not very much more than 2,000 kilograms. Why do I say that? Because Gemini weighed about 2,000 kilograms. That which man has done, man can aspire to do. And if you look at the weight breakdown of Gemini, an awful lot of it was in the electronics racks, which I'm pretty sure we can do something about. So as an example, this is a quick layout of 2 people packaged inside the Mars Science Laboratory aeroshell, which happens to be an aeroshell that we know is a high LRD aeroshell that works. It had about a 700 kilogram weight for the aeroshell, so it is absolutely not crazy to think about packaging what I'll call a 2,600 kilogram object inside that aeroshell. That happens to also be the entryway to the Mars Science Laboratory into the Martian atmosphere. It's tiny. And for various reasons, when you start looking at how things stack together, it helps if it has a couple of docking ports on it, because one of the challenges in putting stacks of missions together is that you run out of docking adapters. And since this thing isn't doing anything most of the mission, it helps if it serves as a docking adapter. That's, I think, probably about the last picture I'm going to use, so I think I have a black page to rest on. So let's start with the moon. I like the moon. I think it's a very economically useful destination. Whether or not you think you personally are excited about it as exploration is not my call. Doing lunar missions to the moon on a minimum scale is enormously facilitated by having the ability to park hydrogen-fueled things somewhere near the moon for a long time. And we can do surprisingly good with Centaur in terms of minimizing the boil-off, but you can't get down to 0. The usual aerospace answer to that is we're going to invent something called zero boil-off storage. That's an expensive technology product. We also have a much more arcane technology called refrigerators. And if you're willing to put up a module that employs some combination of sun shield or some combination of a small few kilowatts refrigerator, you can imagine docking a Centaur or a Delta IV stage to it and having it just stay that way, because you don't have to bring the refrigerator with you every time. You park it wherever your assembly node is. I'll say L1 without loss of generality for the rest of this, but there are certainly other cislunar staging points that you could take. You're going to need some kind of habitat there. Why you're going to need some kind of habitat there? Well, it takes time to phase the missions. It takes time to get all the pieces assembled, and you don't want to live for a long time in a capsule that's not a hell of a lot bigger than Gemini. But that's okay. There's lots of people out there thinking about ways to do very small hab modules. Bigelow's got one that they're putting together, beam for the space station. Inspiration Mars folks have looked at how to do that with a Cygnus module for a Mars flyby mission. These are both, 2,000, 3,000, 4,000 dry mass hulls that only hold a couple of people, but we only need to hold a couple of people. If you put the hab up at L1, which you can do with a Centaur, and if you put The refrigerator satellite, which I think is only a few thousand kilograms up at L1, which you can do with a Centaur, you can now bring a Centaur and its payload up to L1 and park it there, and it's still a propulsively useful thing. You can bring a hydrogen-fueled stage up there, on a lander up there, and ULA has published papers on how to do Centaur-derived lunar landers. Hydrogen changes the game on how much you have to throw away, because you can do single-stage hydrogen from L1 to LEO and back to L1 without getting crazy, without inventing anything new, just by using the same kind of mass fractions you have in a Centaur. And by happenstance, it turns out that if you launch a Centaur and no payload, the Centaur can bring itself and enough hydrogen and oxygen to L1 to fuel a Centaur-sized lunar lander to go from L1 to the lunar surface and back to L1. So for every Centaur launch, you can do one more mission. But it's not quite, but you all have to have another launch to bring the payload for that lander up to L1, or the crew, if it's a crew mission, for that lander up to L1. So I'll say Falcon 9 Dragon as a shorthand for whoever ends up being the commercial crew vehicle. But Falcon 9 is the one that we have the best idea about the price of. So if you were doing a crew mission, that's one Atlas to bring your propellant up, and another Atlas to be ready to bring your crew up, and then a Dragon to bring your crew up. And then the crew moves into the lunar transfer capsule. You pop it up to L1. They board the lunar lander. You go down to the surface and come back. They pop in the transfer vehicle again. They come back. They re-enter in the tiny little capsule. They step out, and the mission is over. Now, what you think it's going to cost to develop that hardware is one of the numbers that you can say anything about, and no one can say that you're right, and no one can say that you're wrong. Certainly, if you did that with NASA cost model, you would say the unit cost is $10 billion of anything. Costs $10 billion to do a thing. So, you know, it's a new capsule, that's $10 billion. It's a lander, that's $10 billion. It's a refrigerator satellite, that's $10 billion. And it's a manned hab, that's $10 billion. You know, and we haven't even gotten into 10 healthy centers yet. So you know, it looks very expensive. If you're a private concern, you say things like, well, I don't need a new satellite bus. I'm just talking about buying a satellite that already has radiators and packaging the components differently. You know, that may not have any NRE at all. You know, the heat shields already exist, so I could buy another copy of it, and it doesn't really cost that much to engineer a pressure can to sit on top of it. So you might think that's very inexpensive, and I can't prove that either of those is right. But I can talk about is the launch cost. It is my belief that the cost of things in space has something to do with the cost of launch. And the reason for that is that if launch is very expensive, it makes sense to put more engineering into making the thing you're launching lighter weight. And if launch is very cheap, it doesn't make sense to put a lot of effort into making the thing that you launch lighter. So I think there's some relationship between the cost of launch and the cost of what it takes to develop the hardware. So in round terms, if you add up what I just said, that's about $720 million in launch cost to set up the mission architecture and do the first mission. And every subsequent mission, manned round trip to the surface of the moon and back, is a launch cost of about $270 million at today's prices. So if you thought that the development NRE cost of this was going to be something like equal to or 2 times what it costs to launch all the hardware, which I don't think is crazy, you're talking about the first manned return to the moon and back for something like $2 or $3 billion. I don't know where we're going to get $2 or $3 billion to do that mission, but that is about 2 orders of magnitude cheaper than we were currently thinking in the government program it would take to do. Maybe somebody can find something useful to do with that. The Mars Flyby mission, which Inspiration Mars is working on, I found very intriguing. I was very excited when that was announced because I thought it was a great mission. And the reason is that, as I've talked before, the greatest unknown by far we have in trying to figure out what it takes to do a Mars mission is we really don't know what the cosmic radiation hazard to human health is. Now, it's a brave thing for 2 human beings to find out by going to Mars and coming back and finding out if they come back. But you'd know after you were done. And that is the way that, and it is arguable whether there is any amount of research we can do for however many hundreds of billions of dollars in decades we might study it that would answer that question in any other way. I mean, sooner or later, somebody's got to go. And I was a little bit surprised when they started looking at alternatives to the existing launchers. And I don't know the insides of their project very well, and I can't speak for what trades they have and haven't done. But it intrigued me, so I dug into the problem. And I discovered that it really is hard. It is hard to figure out how to do the Mars Flyby free return mission within the constraints of existing launchers, but I don't think it's impossible. Again, in round terms, Delta IV Heavy is the biggest Earth departure stage we got. If you launch Delta IV Heavy, depending on how much excess velocity after leaving Earth orbit you need, you can throw something between 14 and 20,000 kilograms leaving Earth orbit with a full Delta IV Heavy. The Mars Flyby mission needs a fairly high velocity after it leaves Earth orbit. So it's a hard mission to do. At first, that looks like a problem, but then I realized after you've left Earth orbit and have reached a safe speed, you're in a good position to use electric propulsion. Normally, that isn't such a big help because it takes such a long time for the Delta V to build up, but whether you like it or not, if you're going to Mars, it takes a long time. I've seen a lot of studies of all chemical or all electric missions. I haven't seen an awful lot of studies of mostly chemical, some electric missions. I ran the numbers, and I was pleasantly surprised to find that if you only ask for another 500 or 1,000 meters per second out of your electric propulsion stage, it doesn't add so much mass to the spacecraft, and it's well within the capability of solar arrays that are in the lab right now. The descendant of the Deep Space One concentrator array. There's a laboratory version of that right now that's a 100 kilowatt array, and that's about what you need. And you don't need to invent new thrusters. You put 12 of the satellite ion thrusters that are in commercial use right now and rack them up. Now, as I said, it only gets you about 1 kilometer per second, but that's enough to bring the throw weight of the Delta IV up to just shy of 20,000 pounds, or 20,000 kilograms, which means even after you deduct for the power system, you can imagine throwing a payload that's on the order of 16,000, 17,000 kilograms to the free return Mars trajectory, which is coincidentally about the mass that Inspiration Mars thought they would need for their stack, minus the difference in mass between the many-person capsule and the two-person capsule. Now, this is a complete mission design? Absolutely not. Or, this is me on the occasional weekend. There's way more that can be done. There's way more that should be done. But I think it's a mistake to look at these things and say they can't be done. I think they actually can be done. And if in a few weekends looking at the available literature, some of these problems can be solved, I bet if more people start thinking about them, and there are other problems, more of those problems can be solved. If you follow that architecture I just mentioned, what does it take in launch cost? Well, you have to get the HAB and the capsule and the service module up. That's an Atlas. You have to get the crew up. That's a Falcon. And you have to get the Earth departure stage up. That's a Delta IV Heavy. That's $620 million in launch cost. Let's do that same rule of say about 3 for the NRE. That's double the cost of the launch cost. That's under $2 billion to do a Mars flyby. At the end of which we would know if human beings can go to Mars cheaply for the rest of time, which would be a useful thing to know. One challenging bit of that is, there's no game without risk. By launching the pieces separately, the Earth's equatorial bulge makes the orbital inclination of the parking orbit that you're in precess. And that means that the Delta IV has to go off on schedule. Whenever you launch the first piece, you have decided the day when the Delta IV is going to launch, plus or minus about a day. You can't get a lot more than that without it cratering your performance to do the plane change. Okay, that's hard. Absolutely, that's hard. But the number of planetary missions that have had tight launch windows and not missed them is very high. And it's certainly easier to invest in increasing the dispatch reliability of launchers that exist than it is to invent new launchers. But, it would be very disappointing to plan a mission like that and have it not go because the Delta IV didn't launch in the 3-day window that it had to go. I understand that. But it's not like we're going anyway. It's not like there's some alternative mission that's currently going to happen that involves going to Mars the better, different way that's much more certain to work. We may face the choice between taking some risk and not going. And it's not like the people have to not live, it just means they have to come home very disappointed. But if that's too much risk for you, there is an alternative. You can, if you've already done the thing of going to the moon, and you already have a hab at L1, and you already have a refrigerator module at L1, instead of staging in Earth orbit, you can stage at L1. Then you launch 2 Centaurs instead of a Delta IV and a Centaur. And if you fill a Centaur at L1, it puts 30 tons on a Mars insertion trajectory, which is way more than you need. You don't even have to fill it, which is why you can do the mission with a smaller number of Centaurs. No, it's more expensive. That'd be a launch cost in the order of $800 or $900 million to do a Mars flyby with schedule flexibility so you didn't depend on going off on exactly the right window. But it's not billions and billions of dollars more expensive, it's just more expensive. I don't like to develop hardware that only lets you go by and not land. That makes me crawl as an engineer. There's nothing wrong with it, it's a great mission. But I would have felt better about the whole thing if I could figure out how to land somewhere, so I looked at that. And you have to arrange the stack slightly differently, but you can do it. It takes 2 of the same missions that more or less that you would do the Mars flyby with, and one of them has to aerobrake the capsule and at a chemical propulsion stage into orbit, into Mars orbit, and from thence to Deimos. And the first mission plants the hab and the return delta V that you need to get out of Deimos orbit and back on Earth return trajectory to Deimos. So that's a very expensive mission. That has a launch cost of almost $2 billion to land the first human beings on the moons of Mars and be in sufficiently close proximity to Mars that you could drive rovers around on the Martian surface in real time, that you could pick up various samples. If there happened to be a government mission that wished to do sample return from Mars, you'd have everything you'd need to do that, and it would be a place that no human being had ever been before. And if you felt like keeping going after this, once you can soft land and cache things on Deimos or Phobos, really nothing except your budget and your patience prevents you from accumulating enough equipment there to land on Mars. It takes more time, it takes more money, and I think it probably would exceed the ability of the private purse unless people started doing in situ resource utilization on Deimos and Phobos and making their own propellant, and then you can do the Mars landing for something on the same order. Not saying it's easy, not saying there aren't many difficulties, not saying there's not a lot of risk, just saying it's not impossible. And let us say, for the sake of discussion, that the optimistic assumptions about galactic cosmic ray hazard that Inspiration Mars wants to make and that I hope are true, let us assume that they are false. Let us assume that the most conservative people are instead right, and you just don't dare leave the magnetosphere of Earth for any significant period of time unshielded, or you're going to die. Okay, now I say again, I don't happen to believe that's correct, but nobody on the planet knows, because we don't have enough data exposing mammalian organisms to primary cosmic rays for enough time to know. Okay, that's a definite problem. The shielding for we've all been told, and I have said, the shielding for galactic cosmic rays is a massive thing. So I was sure when I sat down to do the numbers on this, it would show that would be an insuperable problem for doing it on the cheap, that we couldn't do it. And I was shocked to find that I was convincing myself otherwise. The way you have to do that, clearly, is the hab becomes very massive. You can't keep accelerating it to and from Mars every time. It weighs too damn much. So you have to do a cycler, as I heard somebody correctly say out there. There's many arrays of cyclers, the first of which, of course, is the Aldrin cycler. Thank you, Buzz. But some of the other alternatives have slightly lower delta V to get to and from the cycler, but at the price of having to do 2 cyclers. But you don't have to do 2 cyclers for your first mission. You only have to do 2 cyclers when you're so sure you want to keep doing it that you want to do it every 2 years. And yes, the HAB is massive. That tiny little few thousand kilogram habitat that you can get 2 people in with enough space to get to Mars, becomes 20,000 kilograms if you put 0.2 meters of polyethylene around. Now, 20,000 is a lot bigger, but it's not all the mass in the world. And if you really want to go Cadillac, you put 2 of them together, and you put a 20-meter cable radius in between the 2 of them, and you spin it, and now you have 1/3 gravity to and from Mars, just in case that's a problem. Okay, so what the hell? Let's go Cadillac. You add all that up for 2 people, that's 50,000 kilograms of mass that has to somehow get into an Earth escape trajectory. Bad news. Okay, but we can get 10,000 kilograms up to L1 with every Centaur. That 50,000 kilograms is 5 Atlas launches. It's not science fictional. We could actually do it if we decided to do it. And then you use electric propulsion, which you can use at L1, because you don't care how long it takes the cycler to get into the orbit that it's going. And it takes a lot of electric propellant, thousands of kilograms, single-digit thousands of kilograms of electric propellant to push that into an interplanetary trajectory. And then every time you want to go to it, you still have to spend another Atlas, and another Dragon, because you still got to get the crew up, you still got to put the Earth departure stage on them, you still got to get them up to L1, you still got to depart from there to meet the HAB, okay? But even this, which I think is absolutely the upper bound of what it would take to do a mission like that, you're talking about launch costs I'm on the wrong page here. The launch cost to get each cycler up is about $1.4 billion. And the launch cost to do a mission once the cycler is up to Mars and back is about $540 million. For just launch costs, not the payload, not the whole, there's a lot of extra things to spend money on. I tell you 3 times, okay, I'm not saying you can do these missions for the numbers I'm talking about. What I am saying is if you look at the numbers I'm talking about, I think even this could be done for something in the $5-6 billion range if it was done with the same kind of procurement practices and the same kind of tolerance for risk and the same kind of willingness to think out of the box that a lot of other space hardware has been developed in the last few years. This was a real eye-opener for me. I did not go into this talk expecting to find these things. I expected it to be a doom and gloom talk where I said that that we can settle space privately and that we can exploit what we have found in space privately, but that exploration will remain a role of government. And I say again what I said at the start. It would be a better world if government played a bigger role in resuming the active human exploration of space. We would get more done, we would get there faster, we would get there safer, we would develop more useful things on the way. But if they don't do it, we don't have to stop. Now, in the spirit of what the speech before me, or the panel before me said, I also want to question one of the assumptions. I started by saying, you have to work with the launchers you've got because developing a new launcher would clearly be out of scope. That is not actually obviously the case. Now that we once again are having a competitive launch industry, which is a wonderful development, competition works both ways. All the players work to get better. And there's been a lot of talk since the Augustine Commission days about a thing called ACES, which is an upgraded Centaur, essentially. Now, that's an expensive development item. ULA stated publicly that they thought that would be about $1 billion item. But that's not saying that if you were the customer, you'd necessarily have to pay ULA $1 billion to get it, because they want to build it for their own purposes. Now, what it would cost to be the launch customer of that is an interesting question that I don't think anybody's asked them. But by way of passing, I'll say that if you had such a stage, which is a colossally expensive $1 billion upgrade, you could do the whole Mars flyby mission on one Delta IV Heavy and be done. which is, according to the prices ULA published recently, a $350 million launch, which is expensive for you and me, but on the scale of historical human spaceflight is peanuts. And that is most of what I have to say, except that, again, I'm not a finance whiz. I can't tell you where we're going to get the $2 billion. I can only tell you that we can do it for 1% of what NASA thinks it's going to cost if we do it NASA's way. But I note with interest that of the top 10 grossing movies of all time, 3 of them are science fiction movies: Avatar, Star Wars, and E.T. And if I'm even in the right ballpark, every one of those movies cost more than it would take to do a Mars flyby or a return to the moon, or rather made more money than it would take to do a Mars flyby or a return to the moon. And I know I can't figure out how to do this, but I can't help but think that somewhere on this planet is somebody who can figure out how to make as much money from going to the moon as we made from going to Avatar. Thank you very much. I'm told we have time for 2 questions. Oh, while you're asking the question, my thingy is not working again. Shoot. If you can get to the last slide back there while we're up here, that would be nice. Yes, sir.
If the Delta IV misses its launch target, can't you just take those guys, push them outside the magnetosphere, and get your radiation data anyways?
Yes. That would be an excellent fallback mission.
I'm Pete Humphreys from Humphreys & Associates. You mentioned the movie industry. We have one of the premier guys next door, Dan Curry from Star Trek. You should go and mention him. He'll advocate for all of us. Yeah, he's right next to my booth. I'd encourage you to come by and talk to him.
I absolutely will. And if you could dwell on the last slide of the deck, if possible, while I get off the stage. It's got my footnotes. I brought a talk with footnotes, so if you want to know where the underlying technologies and assumptions for all this come from, I didn't invent them. I had to look them up. Apparently we can't do that. Well, I'm sure we can find some way to make the slides available after. But if you can throw that one last slide up, some people in the audience might be interested. Thank you all very much.